And so if we kind of keep going with this here, there's another representation I'm going to show you with how we can kind of, where the shape is largely coming from. Obviously, we can use a computer to get it for us exactly. But if we look at the radial wave functions, so that's what I have right here, the radial wave functions. So I'll remind you, those are the R, N, L of R functions. So for example, when N is 2 and L is 0, that's R20, which is the 2s wave function, right? And when N is 2 and L is 1, that's the R21. That gives me the 2p wave function, the radial wave function. And so we note that the 2s, and this is not the square, right? We want to see positive and negative values. The positive and negative values of the wave functions are important in molecular orbital theory and in valence bond theory. Okay, so we can see the R2s. I'm going to highlight, right, that it drops down, it drops below, right, there's a node, and then it comes back up and it approaches the x-axis. And now the 2p, it's only positive regions, right? And it's kind of got this almost Boltzmann-like distribution. So let's keep that in mind, okay? And so now these two wave functions, they're flipped on their side 90 degrees, and they're added together. So let's take a look. So here, this blue is my 2s. And check it out. It drops down, it hits that node, it goes below, and reappears, okay? And so then that's just drawn symmetrically about this axis, right? Because we recognize that we can swing these radial functions around to, right, positive R values, or we can swing them around to negative R values. And so that's what's done on this graph right here, right? Then we can see the 2s wave function, but now as negative values, okay? So here's what's important to note, though. When we do the same thing for 2p, when I go and plug in negative R values for R21, it actually flips the sign. And I'll show you that. I don't have the equation in front of you, but I'll just show you that result. Where if suppose, well, it's kind of drawn backwards, but let's suppose that these are my positive values and these are my negative values, right? So here is my positive values of 2p, right? So it just kind of looks like that, that distribution, right? But now going to negative values for specifically the R21, it changes the sign of the function and looks something like that, okay? So now when we add those two things together, we're going to have regions of heightened constructive interference indicated right here, right? Because, and at this point, it doesn't really matter whether it's negative or positive. What matters is that they're both constructively interfering, right? They're both on this side of the axis. So that leads to a large lobe right there, okay? And on this side of the axis, they're on opposite sides, okay? And so the result is destructive interference, which is a much smaller curve that's drawn there. And so when you look at those two shapes, you get a really large lobe looking like this, that's all constructive interference, and you get a small lobe that looks like this, that's all destructive interference. And right, this bigger area right here, right, that was the negative region, and this bigger area right here, that's the positive region. And if you look at my Mathematica model, here I've specifically labeled red as the negative region and green as the positive region. So we can see that. We can see this larger negative region lobe and this smaller positive region lobe, okay? And of course we know that those are, right, the 109, technically 109.47, 109.5 is the angle we all know and love. And here this is only showing you one of those lobes as indicated in this picture, right? But those black lines, right, show you the vector where each one of those lobes would then exist, okay? As given by this guy right here, okay? Very cool stuff. So moving along. And finally, if I want to make a molecule out of sp3 hybridized carbon, okay? Now, finally, I have to have overlap of an empty hydrogen 1s orbital with an empty sp3 orbital. And interestingly, it ends up being the negative region of the wave function that overlaps. That then would have to overlap with the negative region of this wave function as well to give us the chemical bond, okay? Which is pretty cool. Because once again, we only had one electron, where is it? Yes, one electron in each of the sp3s. So to make a bond, and specifically to make a sigma bond, right? Then we have that spherically symmetrical overlap. And so now, because this is not just a simple diatomic molecule, right? We get a coordinate system for each sp3 orbital where there's a hydrogen positioned. So for this chemical bond, right, the one that I'll highlight here, that represents a z-axis coordinate system for that particular one, okay? But if I look down this chemical bond, that makes another z-axis and another z-axis and so on and so forth. So that's where this gets really complicated, because when we put together wave functions for these molecules, we recognize that we have multiple coordinate systems based on our sigma bond, okay? Hopefully that makes good sense. So moving